0 plus 0 is 1.
Yeah, so the identically zero function won't solve.
0.
Yeah. So here I have my easiest example of a non-homogeneous spring type thing. Okay, so what do you do to start with?
Turn into R's.
Yes. Solve that
So,
one.
Solve the homogeneous one by turning it into R's. And then you're going to have to guess. Right?
Yeah.
Like, don't worry, this is not a new technique. It's just executed a little differently. So, first things first, look at the homogeneous version. So the homogeneous version is like y double prime, yh double prime plus yh is 0. How do you solve this?
turn into R's.
Turn it into R's. So you get r squared plus 1 is 0.
R squared equals -1. R equals plus or
So
minus.
r squared is -1, so r is plus or minus I.
We
So,
have the purely sinusoidal.
yep, so you
negative
got
discriminant.
y is c1 cosine x plus c2 sine x. Everybody good with this?
And this is our y homogeneous.
Yeah, this is our homogeneous solution right here. So, then what? And this is where things get a little different.
You have to guess.
Yeah, do not do variation of parameters. Okay?
Okay.
What you want to do instead is look here at the right-hand side. So, writing this out carefully. Consider a function 1. Right? This function is the hard one. It is always 1. And then consider to yourself, what kind of stuff can you differentiate a couple times, add to itself, and still end up with a constant? Yeah, maybe a constant would work. Okay. And that's really what we're doing. We're like, okay, so let me just guess y is 1. Okay, then y prime is 0. Y double prime is 0. If I sub that back in, I get 0 plus 1. And I'm wondering, is that 1? Last I checked. Cool. Okay, so here's what I found. I found a particular solution, right? Which I'm going to call yp. And that solution was 1. And then I would like to stick the homogeneous, oops, that was supposed to be a homogeneous solution, by the way. I would like to stick the homogeneous solution and my particular solution that I found together. Make them one thing. What is an appropriate operation to make these one thing?
Multiplication.
What a great idea. Except it totally doesn't work.
Add them together.
Because if you take yp, 1, right, and multiply by this, you get
Right.
this.
Homogeneous.
And then when you shove this back in the differential equation, guess what you get?
0 equals 1.
0, because it was the homogeneous solution, right? So you try something else, like adding, because duh. Like, because you tried the other one, right? So now you like, okay, so we'll guess y is yh plus yp, right? And then if we shove this in, right, y prime is yh prime plus yp prime. Y double prime is yh double prime plus yp double prime. That stuff there, if you sub it in, is going to give you 0. Why?
Because that's the homogeneous solution.
Because it's the homogeneous, because you made it that, right? Like you made it that way. This stuff if you shove it in, is going to give you
One.
1. And those two things are going to be whatted together?
Added.
Added together. Cool. You guys good with this?
Yes, can we get something slightly more general?
Yeah. So this is what's called the method of undetermined coefficients.
Okay.
Okay?
Yeah.
And what it amounts to is solve the homogeneous version, then make a decent guess about what kind of thing is going to result in that kind of thing remaining. Like basically eyeball the category of your forcing term. Then do some solving, figure out what that forcing term is, and add them together. Or sorry, figure out what a particular solution is, and add them together. Why don't I need to worry about constants for my particular solution? Yeah, in this case it is constant. Your constants for your initial conditions are right here anyway. The homogeneous version already has 2 constants in it. You don't need a third.
Okay, so
Cool.
assuming everything on the right side, like f of x is a constant, then y is equal to your homogeneous solution plus the constant?
Yeah. If everything on the right-hand side is a polynomial, you would guess a polynomial. If everything on the right-hand side is an exponential, you would guess a exponential. If everything on the right-hand side was sines and cosines, you would guess sines and cosines. Right? Because those kind of things remain constant under differentiation, right? Polynomials differentiate to polynomials. Sines and cosines differentiate to sines and cosines. E's differentiate to e's. So,
Okay, when you're doing and the considering you have the f of x and it's to that like polynomial or whatever, does it have to be that specific one, or is it just like a general form of a polynomial? Like if you were doing that.
yeah, good question. So I need a general formula for a polynomial. So let me try this with a slightly more complicated path. So I'm just going to change this right here because I'm low on time. So let me say that this is x plus 2.
Well, it's time we're going to talk about this.
Oh, see? Perfect. I'm super low on time. So if I guess
You were negative 5 minutes.
f is the x plus 2 that I want to see, what kind of thing are you going to differentiate a couple times and still have an x plus 2 kicking around?
Cubic, right?
So if I have a cubic, I'll get a constant kicking around, right?
If you differentiate twice,
You guys see that? Like, if I start with y is ax cubed, then y prime is going to be ax squared.
And y is
Y double prime is going to be
ax.
ax.
Now what we want?
So you need to add a.
You guys see this?
You need to say ax cubed plus bx squared.
Yeah, so you could try this. Give it a shot. I'm out of time, so take something like this, differentiate it a couple times, you'll get a system of equations to solve. You'll probably have way more variables than you need. Solve. In fact, I know here I'll have an x cubed left over, right? Because there's a y right here. So something's going to go away fast. Give it a shot, see what you get.